Organizations are actively pulling large language models into their internal infrastructure to automate complex tasks. But pointing a raw, off-the-shelf model at your internal databases without proper conditioning is the fastest way to make those systems violently break down. A failed enterprise deployment carries immediate operational penalties. It means leaking sensitive customer data, failing external audits, and generating compliance violations that carry severe legal fines. To eliminate those risks, you must use a rigid 14-step fine-tuning and security validation lifecycle. This is the mandatory operational blueprint to safely push any customized model into a production environment. Before starting step 1, you need 3 prerequisites in place: a raw dataset containing your domain knowledge, adequate compute resources to handle the processing load, and access to a reliable model hub. With those in place, the work begins. Pushing a model to production requires strict discipline, treating the AI pipeline as a rigorous end-to-end security and compliance operation. Phase 1 covers the first 3 steps. The primary objective here is to legally and technically secure the foundational architecture before committing any engineering resources. Step 1 is selecting the base model. You must evaluate the enterprise use case and strike a precise balance between total parameter size and baseline language capabilities required to execute the task. Step 2 requires confirming the model license. Open weights does not automatically grant you the right to commercial deployment. You must verify that the model operates under a permissive license, like Apache 2.0 or MIT, to avoid legal roadblocks later. Step 3 is importing the model weights. The engineering team mechanically downloads and transfers the chosen architecture from the public hub directly into the enterprise's private isolated training environment. Skipping these foundational legal and technical checks guarantees failure. If the license is restricted, any downstream training effort becomes legally non-viable for enterprise deployment, wasting all invested compute time. With the foundation secure, Phase 2 prepares the data and configures the hardware engines. Step 4 is creating the training dataset. You must structure your raw, unstructured domain knowledge into specific prompt and completion pairs so the model can process the desired logic. Step 5 introduces the first critical security checkpoint: data de-identification. You must aggressively scrub the training data. Real personal names and financial records are removed entirely and replaced with generic tags to ensure sensitive information never enters the training weights. Step 6 dictates the hardware logic by selecting the tuning method. If you are operating under single GPU limitations, you configure QLORA to compress the memory footprint. If you have access to large multi-GPU clusters, you allocate FSDP to distribute the load. This chart tracks training loss over time. During Step 7, the actual execution of the fine-tuning, the engineer monitors this exact metric to verify the model is actively learning the prompt completion pairs, looking for the line to smoothly trend downward and stabilize. Perfectly formatted, sanitized data combined with precise compute allocation prevents fatal out-of-memory errors and eliminates data poisoning during this active training run. Phase 3 shifts the focus away from active training and into objective capability validation. Step 8 performs a validation evaluation. You test the model against a holdout dataset, information it was never trained on, to confirm it is generalizing the underlying concepts, rather than merely memorizing its training data. This radar chart maps the results of Step 9, the test set evaluation. By scoring the analyzed model on entirely unseen data across axes like accuracy, fluency, and relevance, you measure its actual operational fluency. The model must be mathematically verified as capable of performing its assigned task before you commit operational resources to the rigorous security stress tests that follow. Phase 4 introduces the adversarial stage. The objective shifts from helping the model succeed to intentionally trying to break its guardrails. Step 10 is the red team set testing. Security engineers hit the model with malicious jailbreaks and adversarial prompts, verifying that the system safely rejects harmful commands. Step 11 is PII leakage testing. The team specifically tries to force the model to regurgitate sensitive data. Passing this test proves that Step 5's data sanitization was executed correctly, and no protected information exists in the weights. Step 12 executes compliance answer consistency testing. This verifies that the model's responses strictly adhere to the company's internal legal guidelines and operational policies across a wide range of queries. A highly intelligent model that fails these security checks remains a massive enterprise liability. Passing this adversarial phase serves as the absolute gatekeeper for deployment. The final phase manages the bureaucratic documentation required to push the system live. Step 13 requires a model signature and model card. The engineer compiles training metrics, hardware configurations, and security results into a standardized document, which is cryptographically signed and logged in the internal registry. Step 14 is the deployment review. The completed model card is handed off to the Enterprise Security Board, allowing them to review the quantified metrics and make the final go or no-go decision. The comprehensive model card serves as the unassailable, auditable proof required to confidently authorize the system for a live production environment. With all 14 critical steps successfully executed, the custom model is now safely active in a live enterprise setting. A raw foundation model is highly capable, but entirely unguarded. By routing it through this exact sequence, you strip away the vulnerabilities and produce a hardened, compliant asset safe for internal reliance. This exact 14-step methodology is highly repeatable. It provides your engineering teams with a permanent operational blueprint for all future fine-tuning initiatives. Download the complete 14-step checklist in the description below, and subscribe to the channel for more comprehensive breakdowns of enterprise AI engineering. Structural rigor and uncompromising validation processes are the exact mechanisms that safely convert experimental AI into permanent enterprise value.